9 worlds in our own solar system could already host life, and we're ranking them from longshot to likeliest. NASA astrobiologists currently list 9 bodies inside our cosmic neighborhood where microbial biology is not only possible, but quietly plausible right now. Not billions of years ago. Not after terraforming. Today. These are not exoplanets 500 light-years away. They are moons you could point a telescope at tonight, dwarf planets hiding liquid water under crusts of ice, and one poison cloud deck close enough to see with the naked eye. Each one carries a real, peer-reviewed case for harboring something alive. Some are desperate longshots kept on the list out of scientific caution. One has evidence so specific that mission teams are already designing the probe to confirm it. We will work upward through all 9. This is about life we have never formally discovered, only failed to rule out. Here is the unsettling part. Most of these worlds are not borderline. They are not maybe in a billion years. Their environments match conditions that on Earth produce thriving microbial ecosystems within weeks. Hydrothermal vents, brine pockets, sealed subsurface seas warmed by tidal friction, radiation-shielded ice shells acting like natural bioreactors. If life is even half as stubborn as Earth biology keeps suggesting, several of these places should already be inhabited. That is not speculation. That is what extremophile research keeps implying year after year. And yet, every time a probe gets close enough to look carefully, we find something we did not expect: plumes that should not exist, chemistry that should be balanced but is not, heat sources whose origin we still cannot name. The list of 9 is not stable, it grows. Scientists quietly add worlds to it. They almost never cross one off. That pattern alone should make you nervous. Number 9 is Triton, Neptune's retrograde moon. Triton is a long shot for one strange reason: active nitrogen geysers erupting on a world where surface temperatures hit -235°C. Those geysers hint at internal heat, and internal heat means possible subsurface liquid. We have exactly one flyby, from Voyager 2 in 1989, and nothing since. Number 8 is Ceres, the largest object in the asteroid belt. The Dawn mission found bright salt deposits leaking from Occultator crater, remnants of briny water reaching the surface within the last few million years. Ceres is small, but it is wet, and it is recent. Number 7 is Callisto, Jupiter's quietest moon. Beneath a 100-kilometer ice shell, magnetic field measurements suggest a salty ocean. Callisto is battered, ancient, almost boringly stable, which is exactly why some astrobiologists argue slow chemistry has had 4 billion uninterrupted years to do something strange down there. Number 6 is Ganymede, the largest moon in the solar system, bigger than Mercury itself. Hubble observations of auroral flickering confirmed a subsurface ocean containing more water than all of Earth's surface seas combined. The catch: it may be sandwiched between 2 layers of high-pressure ice, sealed away from any rocky seafloor chemistry. Number 5 is Venus, specifically a thin cloud layer 50 kilometers above the hellish surface where temperatures and pressures almost match sea-level Earth. The controversial 2020 phosphine detection is still disputed, but nobody has fully ruled it out. Number 4 is Mars. Forget the surface. Recent radar surveys suggest liquid water lakes beneath the south polar ice cap, briny and freezing, but possibly stable. Mars keeps refusing to stay dead. Number 3 is Titan, Saturn's orange moon where rivers of liquid methane carve real landscapes. Titan may host exotic chemistry, life that does not need water at all. That leaves 2, and the gap between them and the rest is enormous. Number 2 is Europa, Jupiter's smooth-shelled moon whose subsurface ocean contains roughly twice Earth's total water volume and rests directly on warm rock. Europa Clipper, launched in October 2024, is already on its way to confirm whether that ocean is habitable. And number 1, the single best bet scientists have right now for finding life we have not yet discovered, is Enceladus, Saturn's tiny cryovolcanic moon. Cassini flew through its south polar plumes and tasted the ocean directly. What it found was not ambiguous: liquid water, a rocky seafloor, molecular hydrogen in quantities consistent with active hydrothermal vents, and complex organic molecules including amino acid precursors. Every single ingredient Earth life needs to start, all of them confirmed, in a plume shooting 400 kilometers into space. Enceladus is not a candidate. It is a crime scene waiting for a detective. The reason Enceladus beats Europa comes down to access. Europa's ocean is locked under 15 to 25 kilometers of ice. To sample it, a future mission would need to drill, melt, or wait for a rare natural eruption we are not even certain occurs. Enceladus does the work for you. Its ocean sprays itself into orbit continuously through 4 giant fractures called the tiger stripes. You do not need to land, you do not need to drill, you need a spacecraft flying through a geyser with a good mass spectrometer, and you have a sample of an alien ocean sitting in your collection tray. Cassini, designed in the 1990s before anyone even suspected the plumes existed, still captured silica nanoparticles that can only form when hot water contacts specific rock at temperatures above 90 Celsius. That is not theoretical habitability. That is active, ongoing hydrothermal activity 1.5 billion kilometers away. The dread sets in when you do the numbers. Enceladus is roughly 500 kilometers across, small enough to fit inside Arizona. It should have frozen solid 4 billion years ago. It did not. Tidal flexing from Saturn keeps its core warm, and that warmth has been stable for longer than complex life has existed anywhere on Earth. 4 billion years of liquid water, rock chemistry, and organic molecules, in perfect darkness with nothing to interrupt the process. If that environment produced nothing, then Earth's origin of life story is luckier than we ever suspected. If it produced something, we are about to meet a second, fully independent example of biology, one that evolved in total isolation with no connection to anything in our own tree of life. Scientists call that finding a second Genesis. It would rewrite biology on the same day it is announced. Enceladus is where that question gets answered. The mission to finish the job is already in planning. NASA's proposed Enceladus Orbilander, currently ranked a top priority in the latest Planetary Decadal Survey, would orbit the moon, fly through the plumes repeatedly, then land on the surface near the tiger stripes to sample fresh ice for biosignatures. Launch window opens in the late 2030s. Arrival mid-2050s. Within our lifetimes we will know. Parallel efforts matter too. Europa Clipper reaches Jupiter in 2030 and will conduct 49 flybys, some passing as low as 25 kilometers above the surface. ESA's JWST mission arrives the same year to study Ganymede's ocean. The Dragonfly rotorcraft is scheduled to fly through Titan's skies in 2034. 4 of the 9 candidate worlds will have active reconnaissance missions inside the next decade. No generation before ours has been this close to answering the oldest question humans ask. And none of the answers arriving are going to be quiet. Here is the strange thing nobody mentions. Every world on this list was discovered to be potentially habitable within the last 30 years. 30 years ago, the list was 0. Extrapolate that curve outward. The next generation of telescopes, the Habitable Worlds Observatory, the extremely large telescope, the successors to JWST, are designed specifically to hunt for biosignatures on planets around other stars. They are already finding worlds that look disturbingly Earth-like, closer than anyone predicted they would be. One of them, orbiting a star you can see from your own backyard, carries a water vapor signature in its atmosphere that scientists cannot yet explain away. It did not